This video is going to discuss selected topics on statistics. A lot of the figures are from the Harris textbook, Quantitative Chemical Analysis. On the bottom of each of the slides, however, will be corresponding sections. We leave the page numbers for David Harvey's Analytical Chemistry 2.0 textbook, which is free online. The purpose of showing this slide is to point out that the normal distribution, or the Gaussian bell curve that is commonly used in statistics, is often a good approximation for real data, but isn't the best. So this figure from Harris shows the lifetime of different light bulbs in hours, and you can see that there's an average value, which is marked at the very top of the curve there. The mean, or the average, is being described as X bar with a little line on top of it. And so on average, these light bulbs lasted 845.2 hours. The spread is described by standard deviation, and that's abbreviated S, which is equal to 94.2 hours in the case of this data. The plot on the left here shows two different distributions of, again, light bulbs. And the black line is showing a narrower standard deviation, where you've got 47 hours, versus the blue line, which is a shorter and fatter curve with 94.2 hours. On the right-hand side of the slide is a summary of the most common calculations. So you have your average or mean, which I think many of us know how to calculate from heart. And then the standard deviation is there as well. And so you're going to take the difference between an individual reading and the average, square that difference, add all those squared differences up, divide it by n-1, which is called degrees of freedom. A reminder here, n, the little n, is equal to the number of readings in the sample set. And it's also worth noting before we go forward that the terminology of variance is equal to the standard deviation squared. The last thing to point out is that on those curves on the left-hand side, the same number of light bulbs was measured for each of those curves. And so you can see the relationship between a broader standard deviation for the blue line making a shorter peak. And this is useful in analytical chemistry because it often means that a tight, narrow standard deviation means a nice tall peak. In my particular class, I'm not going to ask you to go in depth with calculating the area under the curve of different regions. The figure on the top right, though, shows the standard bell distribution, the Gaussian curve. And the x-axis is the number of standard deviations from the mean. So the center there is 0, no standard deviations away. And then you've got lines at 1, 2, and 3 standard deviations away from the mean in both directions. That big table is giving us the absolute value of the number of standard deviations from that mean. Y is going to be the intensity, so the count there. And then the area is going to be between 0 and that point. And so the numbers in blue, that's the even numbers of standard deviations. So you've got in the first column there 1 standard deviation away, which has an area of 0.34. And that's going from 0 to 1 in one of the directions. If you go plus or minus 1, then you're going to be doubling that 0.34, which is a fraction now of 0.68. And that gets us to this conclusion that 68.3% of the area is within 1 standard deviation of the mean. And similarly, 95.5% is within 2 standard deviations. And if you go out to 3 standard deviations from the mean on either direction, you're getting 99.7% of the data on a Gaussian curve. This is helpful to know these numbers because we often have to choose what kind of error bars we put on our data. We can pick to calculate the standard deviation and then do an error bar of 1, 2, 3, or other intervals of standard deviations. And the number matters. So if you want to be really discriminatory between different samples, you would pick a 2 sigma or 3 sigma thing. Now, on this particular slide, you'll notice I've got mu plus or minus 1 sigma, and on the last slides I had x for the mean, and I had s for the standard deviation. I'm not going to get into it a lot, but true statisticians will go into the details of the population mean, which would be mu, versus the sample. So the population is all of the individual samples that are out there. The sample that you take and actually measure, though, is going to be x. The sigma here is going to be the population standard deviation, and the little s is going to be the sample standard deviation. So in all of the calculations that I'm discussing, you want the sample mean and the sample standard deviation. I show you this because some of you may be curious about going through the area tables on the previous slide, and so you could figure out and reproduce the two areas that they're showing here, or if you go from minus infinity on this bell curve, which would be a lifetime of 0 hours, up to the 900 hours, you can figure out how many standard deviations from that mean it is and get the overall area. One of the most important things to do when you're looking at your data is to do a quality control check. And by that I mean you want to look at your data and see if there are any outliers, anything that seems pretty spread out. So in the top left of this slide, we see a plot where we have each little circle being an individual reading on a scale. And you see that far left dot is pretty far away from the cluster of the rest of them, and the mean of that data set is labeled there. One of the ways that we can test for outliers to see if that questionable value is really different from the rest of the sample set is to do the Grubb's test. The Grubb's test is going to be taking the difference between that questionable value and the mean value. Take the absolute value of that difference and divide it by the standard deviation. That's going to be called G calculated, G for Grubb's. And then on the right-hand side of this slide, we have the table of Grubb's values. And so the dark blue column is n, the number of measurements. So in this case, we've got what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 measurements. And so you'd go down to 12 measurements there, and then you'd have to pick a confidence level. And so you would say, okay, I want 95% confidence, which is going to be a sigma or a p value of 0.05, and we'd say, okay, the G table is 2.412. And once you calculate out the G calculated value, if that G calc is greater than G table, that's saying that you should discard the questionable value. If G calc is less than or equal to G table, then you would keep the questionable point. It's not an outlier. This relationship between a calculated value and a table value is going to be constant over the course of all of these statistical tests. So anytime your calculated value is greater than the table value, that means that we have something that is different. An older and sometimes more popular way to test for outliers is the Q-test. In the case of the Q-test, you need to organize your data in order of increasing value. So on the bottom there, we've got all of the data lined up. And then you're going to do Q-calc is going to be the gap over the range. And you can see the gap is going to be the difference between the questioned point, which is marked red here, and the nearest value within the whole set. And that's why it's helpful to arrange the data in order of increasing value, is it makes it easier to see which one the nearest value is. So that gap is going to be over range. Range is the total spread, so that's going to be the high and the low of your data. Again, if Q-calc is greater than Q-table, discard it. If it's less, keep it. For your reference here are the critical values for the Q-test. This is what is meant by Q-table. Again, along the left are the number of different measurements, and on the top are the different confidence levels. So a sigma or p-value of 0.1 is going to correspond to 90% confidence, 90. 0.05 is going to be 95% confidence, and so on. Confidence intervals are pretty handy, and for my students, you're going to want to memorize this equation. We use confidence intervals for a couple of things. The first one is it's a nice way to provide error bars on the data, so that you're not just using standard deviation. You can say, here's my error bars to 95% confidence, or here it is to 90% confidence. And then, as I'll discuss a little bit later, we can use this to compare the measured data to a real value or a hypothetical value that we're testing against. So the confidence interval is defined as the mean value plus or minus t times s over the square root of n. We know that s is our standard deviation of the sample set. We know that n is the number of samples or data points. And this t is the student's t-test value. And you're going to go to that table and select t with degrees of freedom, which in this case will be n minus 1. For your reference, the student's t-test table is here, so you can always come back to this video and pause it right now if you need it. And so we have along the list the degrees of freedom, and then we have different confidence levels. Notice that this table is from a different source. Instead of having 0.05 for 95% confidence, it is actually just listing 95 in that blue column. The confidence interval being divided by the square root of n means that the greater the number of measurements you make, the greater the n, the larger that denominator is, and the smaller the confidence interval will be. So what's shown here on the left-hand side is a spread of values. The mean is labeled. And then you've got plus or minus standard deviation in this box going from left to right that's white. If we only had 5 measurements, the 95% confidence interval could actually be worse than the standard deviation because that blue box is wider. However, if you increase the number of measurements, it narrows the range for your confidence level, which is good. And so your 95% confidence level could actually be less than a standard deviation. And that's kind of the beauty of the confidence levels. On the right-hand side, we have bars where the blue range going up and down now is your 50% confidence interval. And so you have a 50% chance that your real value lies within that range. The black vertical distance is your 90% confidence level, and so you have a 90% chance that the true value is in that interval. This chart is again from the Harris book, and what's being shown here is that the center horizontal line is the average, or the known value. And then this is a whole bunch of different trials. The top is showing 50% confidence intervals. The top is showing 90% confidence intervals, which are wider. And every time that one of the dots is filled in black, it's not getting the correct answer. So the correct answer is if your data point, the square, plus or minus its error bars, overlaps with the true value. The purpose of showing this plot is to really illustrate for you how important it is to set a higher confidence interval if you want to be sure that you're including the true value. Now to significance testing. The significance testing means that we're asking a question. Are these two things statistically different or statistically equivalent? Phrased another way, we're asking the question of whether the difference between our values can be explained by random error or indeterminate error. The null hypothesis says that random error can explain the differences and that the values are not significantly different or that they're equivalent. The alternative hypothesis says that the differences are actually too great to be explained by random error, and so they are significantly different. The way we go about this is we set a confidence level, and then what we're going to do is test the null hypothesis. We will either reject it, meaning that, okay, they're significantly different, or we're going to fail to reject it, which is often called accepting it, saying that they are equivalent. In a lot of these tests, you're going to find different tables on the internet, or you might find a different value given through an Excel sheet of the one-tailed and two-tailed tests. On the graphs on the left here, the top is showing a two-tailed test. What that means is if we're talking about 95% confidence, we're going to be wrong 5% of the time, okay? And of that 5% of the time, for a two-tailed, you split it. So 2.5% of what you miss is on the high end and 2.5% is on the low end. Almost all of the time, you want to use the two-tailed test. It's usually the right choice. In the case where you have a particular reason to believe that one of the values you're testing must be larger or smaller than the other, then you would use the one-tailed test. And in that case, you're going to put the whole 5% of that error on one side of this bell curve. Okay, most of the time we're trying to compare average values. We'll have a set of data and we want to know something about it. What I'll call case 1 here is if we're comparing a measurement with a known value. This happens a lot in healthcare and environmental, and also in quality control. So in environmental, you might have a standard where the EPA says you can't have less than 10 ppm, you can't have more than 10 ppm. So you measure your samples and you're like, okay, we've got a range. Does it include the 10 ppm? Is it higher or lower? So the question is, does your measured value agree with the known value or the value of importance within experimental error? We already talked about the confidence interval. The way that you approach this is to simply calculate that confidence interval at your chosen level, example 95%, and then see if that range includes the known value. If the confidence interval does include it, then they're equivalent. If the known value is outside of the range, then your measurement is statistically different. When you're doing this, just as a reminder from a few moments ago, make sure that you get the t value off the t-test table using n-1 degrees of freedom. In a lot of cases, we don't have a known value that we're comparing to. And so if you don't have a known value, then we're really thinking about the consequence of different variables. In that case, you have to determine whether your data is paired or unpaired. It's easier to identify paired data. Paired data means that within the set of samples, you have had every single sample measured multiple ways. An example from the Harvey book is you have 10 pennies and you weigh all 10 of those pennies on a balance and you keep a chart of the mass of each of the 10 pennies on both balances. This is paired data because you have the same 10 pennies on each balance. Another example would be if you had students in a class and you wanted to see if their performance on a quiz predicted their performance on a test. It's paired data because the measurements, the quiz and the test, are made on the exact same samples, students, and you know which one's which because they're labeled. They've got names. In contrast, we have unpaired data. This is when different samples are measured by the different instruments. And so in this example, if we still had 10 pennies and we were trying to compare balances, we would divide the pennies into two groups of 5. We'd weigh 5 pennies on one of the balances, the other 5 on the other balance. Because none of the pennies were weighed on both balances, this is unpaired data, and so we have different math. I'll discuss the unpaired calculations first because this is really the more common type of comparison of means. So we call this case 2, and this is the unpaired data. I'm trying to figure out, are these two sets of samples equivalent to each other? When we say are the sets equivalent, we usually are talking about the average values. Do they have the same average value? The challenge here is that for unpaired data, we actually have 2 unpaired t-tests that can be used. The other challenge is that usually it's not even called unpaired t-test, it's just called t-test. So one of the options is when the 2 sets of data have equivalent standard deviations. The other is when they don't have equivalent standard deviations, so they're different. So the first step is we have to do something called the f-test to figure out if those standard deviations are the same or different. That allows us to proceed to step 2, which is to do the appropriate unpaired t-test for either equivalent or different standard deviations. Point out here that the f-test is comparing standard deviations. The t-test is comparing means or average values. Walking through this then, the first step of doing the f-test, the f calculation is really simple. On the right-hand side, you see it right there. F calc equals standard deviation of the first set of samples squared over the standard deviation of the second set of samples squared. A lot of times, people will say this is the f-test to compare variances. Remember, variance is standard deviation squared. So it's variance of set 1 over variance of set 2, because that s squared is variance. The super important and fabulously important thing right here is that you have to set up this ratio so that f-calc is greater than 1. That means the bigger standard deviation or the bigger variance has to be on top. Like with a lot of our outlier tests, if the f-calc here is bigger than the f-table, then the variances are different. This means we reject the null hypothesis. Here is your f-table. F-table is a little harder to read than some of the other things because you have 2 sets of data and you have 2 standard deviations. The left-hand side is showing the degrees of freedom for standard deviation 2. And on the top, you have degrees of freedom for standard deviation 1. Remember that standard deviation 1 is the one with the bigger variance. Degrees of freedom here is n minus 1. So if you had one set of samples that had 8 samples in it, then its degrees of freedom would be 7. If your other set of samples had 6 samples, degrees of freedom would be 5. If the one with 8 had the bigger variance, you'd go along the top row of the blue numbers until you reach 8. Okay, so that's 8 samples. Go to 7 for n minus 1. Come down to 5 because that's the n minus 1 of the other, and your t-calc is going to be that 4.88. Okay. This slide's a little busy. Calm down, and I'll walk you through it. What you've just done is figured out, are the standard deviations equivalent or not, using the f-test. Now you have to figure out if the means are equivalent. Don't forget this stuff. This is actually what you're trying to figure out. What's shown here is on the top, the mathematics for if you have the same standard deviations. On the bottom is different. I highly recommend that you don't put yourself through the experience of calculating these by hand. You can use Microsoft Excel to use the t-test values. One is t-test, 2 sample assuming equal variances, and the other one is assuming unequal variances. I have a separate video that walks you through how to do that in Excel. With these, again, if t-calc is greater than t-table, the results are considered different. With this thing, if you are doing it manually, though, it's important to recognize that the degrees of freedom for t-table are obtained by adding the number of samples for both data sets, so n1 and n2, and then you have to subtract 2 from that for the degrees of freedom, because there's 2 sample sets. Okay, last slide, last scenario. What if your data is paired and you want to compare the means? Well, this describes how to do that. T-calc, in this case, at the bottom of this slide, is equal to the absolute value of the differences between the samples. So remember, you have, essentially with paired data, a chart where every sample has a reading from one method and the other. You calculate the difference between those two methods. You calculate the average of the differences, take the absolute value of the average of the differences, take the standard deviation of the differences, and then multiply by the square root of n. When you do use the t-table, make sure that you get t-table for n minus 1 degrees of freedom. I highly recommend that you go over to the other videos in the playlist, which show you how to go through with Excel and set up some of these manual equations into Excel to make it easier for you. I hope this was helpful, and have a good time.